Okay, so in this video, I'll do a couple more problems from the determinants section, and I want to emphasize insight. There's a difference between mathematics and calculation. Calculation gets you the answer. Mathematics tells you why the answer is what it is. And so this problem, you can calculate and verify the conclusion, but why? Why is this working? That's a big question, and that's what mathematics is supposed to answer. Okay, so here's the question. The cross product of the two three-dimensional vectors, x1, x2, x3, y1, y2, y3, okay, three-component vectors, and they define the cross product as a vector, and that vector is computed as a determinant. Now, this looks a little bit strange because you're putting a vector in a component as a component of a matrix. So this is just a notational way of showing things. I'll explain what this means in a minute. All right, so let's explain what this means. All right, what this means is that really you should think of this result, since this is a vector, it has three components. The first component is found by taking the first component of all these vectors. The second component is found by taking the second component of all these vectors. And the third component is found by taking the third component of all of these vectors. All right. So what is meant by this is you take the determinant. So the determinant of this thing here, E1, E2, E3, X1, Y1. Right, X1 and Y1 are not vectors, they're numbers, X2, Y2, X3, Y3. Okay. So what you want to think of this is a three-component vector. The first component is when you take the determinant and you take the first component of each vector in the matrix. So the first component of the vector in each matrix, first component of E1 is 1, first component of E2 is 0, first component of E3 is 0. This is just a definition, right? It's kind of not very clearly specified, but that's what is meant here. And then here you have Y1, Y2, Y3. Okay. So that's the first component of this determinant, which is a vector. Second component, well, I take the second component of each vector, 0, 1, 0, x1, x2, x3, y1, y2, y3. Right. Third component, well, third component of each vector here, 0, E1 has third component 0, E2 has third component 0, E3 has third component 1. Okay. If we were really doing this formally, we would have to define the determinant of this in this way. That the determinant really is it really means a vector, and that you break it down by components. Okay, so this is the meaning. So I can say this is actually definition. Okay. That's what is meant by this symbol. All right. So why is this perpendicular to x1, x2, x3? So that's the big question. Why? Why is this perpendicular to x1, x2, x3? Okay. Well, suppose I put a x1, x2, x3 in the first row of my determinant, right? If I put a x1, x2, x3 in the first row of my determinant, then I'd have two linearly dependent rows, and the determinant would be 0. So what we're going to do is show that this perpendicularity condition actually leads to the determinant of x1, x2, x3, x1, x2, x3, y1, y2, y3. So the linear dependence condition is what's giving me the perpendicularity condition. Okay, so suppose I go ahead with this. So what I want is I want to take what is x1, x2, x3. What is this vector? dotted with the determinant, with this determinant expression here. I'll just do dot, 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 and this is y3. Okay. All right. So just this determinant up here. I'm just saying, putting that in shorthand. So how do you do that? Well, you're going to take x1 times the determinant times the first determinant, 1, 0, 0, and then this is the same, right? Plus x2 times the second determinant, 0, 1, 0, and then this is all the same. I'm just trying to save a little time here. There's no real need to write that out again because it's just very repetitive. And x3 times the determinant of 0, 1, 0, 0, 0, 1, and then the determinant. Okay. All right. So what about these three terms? Now, notice we know something about determinant. We know that if we multiply one row of the determinant, that multiplies the determinant by the same number. So this x1 times the determinant here is actually equal to, I can bring the x1 in. So let me just say that. So recall that if I take some number times the determinant of a matrix that's R1, R2, R3, where these are three rows, that's equal to the determinant of AR1. Now I could actually multiply any of the rows, but I just multiply one row. I don't multiply R3 rows. If I multiply all three rows, I multiply the determinant by A cubed. But if I have A times the determinant of a matrix, I can bring that in and multiply one row of the matrix by that constant. Right. So I'm going to use that. So sorry, this is separate over here. Okay. Right. So recall that fact. Then I can rewrite this. So my expression here is then equal to a determinant of x1, 0, 0, and then this is the same, plus determinant of x0, x2, 0, determinant, plus the determinant of 0, 0, x3, and then this here. Oops, sorry, I don't know what that's doing there. All right, so, all right, now we want to use the row expansion property. Now, it's true that in this section of the book, we didn't have the row expansion property yet, but the row expansion property is a key property, very useful property of determinants, that the determinant of, if I have A, B, C in the first row, that's equal to the determinant of A, and then here, A0, 0, plus the determinant of 0, B, 0. I can expand along this row, plus the determinant of 0, 0, B, 0, 0, C. Okay. So what do I have here? Here I have the three terms, which are exactly the row expansion of the determinant where x1, x2, x3 is the first entry. Okay, so I'm going to be using this row expansion property. Based on the row expansion property, I can say this is equal to the determinant of x1, x2, x3. Okay, I'll put the dot, dot, dot here. Now remember what the dot, dot, dot was. This is determinant x1, x2, x3, x1, x2, x3, y1, y2, y3. Okay, and that's equal to 0. Okay, all right, so that's really why this is working, because you're taking advantage of this row expansion property and the fact that if you have a matrix with two rows equal, the determinant will be 0 because those two rows are linearly dependent. I just wanted to make one notice about this concept of cross product. You have a cross product in 2 dimensions that gives you a third vector that's perpendicular to those two. What about 4 dimensions? Do you have a cross product in 4 dimensions? And the answer is no. And the reason is, if I have 2 vectors, then there's not a unique vector that's perpendicular to those two. Rather, I should say there's not a unique vector direction that's perpendicular to those two. So that's why there's no cross product in 4 dimensions. There is an analog. You could take a three-way product where you take 3 vectors in 4 dimensions and find the vector perpendicular to that one. That would be possible, but the binary cross product is particular to 2 dimensions. Okay. All right, I'll stop this video here.